All right, welcome back, everybody. Today we're going to be doing section 7.2, which is all about the law of sines. And just a little bit of a fair warning, this section is a bit technical. The law of sines can lead to many different possibilities of triangles. So this is one of the reasons that I wanted to push it a little bit later. But let's pull up the slides and take a look, and we'll get started. Okay. So first thing we're going to talk about what oblique triangles are. It's just a pretty simple definition. Then we'll talk about solving a triangle again, which is something that we saw in section 7.1. Then we'll get the law of sines, which is what the whole section is about. And then we're going to talk about solving some specific cases of triangles, in particular SAA or ASA triangles, and then SSA triangles. And those types of triangles are called the ambiguous case, and we'll see why when we get there. And then lastly, we'll finish up with an application. So let's start with this. What is an oblique triangle? If you've got a triangle and none of the three angles are right angles, then we say that the triangle is an oblique triangle. So when you have this situation, there are going to be two possible cases. There will be one where all of the angles of the triangle are acute, or two of the angles will be acute and one of them will be obtuse. This is an obtuse angle right there. So we're going to be dealing with triangles of any type, really. But these are the two that we're going to see the most in this particular section. So one thing we got to recall is what solving a triangle means. If you remember from section 7.1, solving a triangle means to find the lengths of all three sides and the angle measures of all three angles. So that's still the goal with this section and with this law that we're going to get, the law of sines. And one theorem that we'll often use is this one, that the sum of the angles of a triangle must add up to 180 degrees. So that we'll use that result quite a lot, actually. Okay. Oh, there we go. Oh, yeah. So in order to solve a triangle, we have to know at least three pieces of information about the triangle, including the length of one side. So this was one of the questions that we were asking in the previous section, right? Like, how much information do we really need to be able to completely solve a triangle? So we need at least three pieces of information, and one of those pieces of information must be the length of one of the sides. So once you have these three pieces of information, this splits the problem of solving a triangle into four possible cases. And here they are. So you might know one side and two angles, ASA or SAA. You might know two sides and the angle opposite one of the sides, that's SSA. Or you might know two sides and the included angle, that's the angle in between the two sides. That's known as the SAS case. And then if you know all three sides, that's the SSS case. So those are the four possible cases we have when we have three pieces of information, including one side. And here's a visual representation of what all of them are. One thing I'll point out is that the information we know is marked in blue on this picture. So let me switch to a blue highlighter here. So case one has two possibilities, ASA or SAA. So in this part, case one would mean that we know one side and two angles. So the side is like sandwiched between those two angles. The other case is we might know one side, one angle, and then another angle that's opposite the side. So that's SAA. And those are the two sub cases of case one, you could say. And the idea is that with those two cases, we know two angles and we know a side. Okay, now let's look at the other cases. Oh, there we go. Look at the other cases right here. My pencil's a little bit slow here. SSA, so in this case, we'll know two sides and one of the angles. And then case three, SAS, that's where we know two sides and we know the angle included in between them. Or we might just know all three sides. So side, side, side. There we go. But none of the angles. So those are all four of the cases, and then the two subcases for case one. The first two cases are what we're going to deal with today. The law of sines lets us address those two cases. So for this lecture, we're only going to be looking at triangles where we know two angles and a side, or we know two sides and an angle opposite one of those sides. So that's what we'll do today. The other two cases, cases 3 and 4, those are addressed by the law of cosines, and we'll get to that on the next section, section 7.3. Okay, so let's get the actual law itself. The law of sines says this: if you've got a triangle with side lengths A, B, and C, and opposite angles A, B, and C, respectively, then we have this set of equations. Sine of A over A is equal to sine of B over B, which is equal to sine of C over C. And one thing I'll point out is that these equations are all transitive, meaning you can look at it like this, or you can look at it like this, or you can look at it like this. That's the idea. So this equation here is relating all three of these quantities: sine of A over the length A, sine of B over the length B, and sine of C over the length C. And it turns out that all of those things are equal. And in practice, what we'll do is we'll basically pick one pair to help us solve for a missing quantity. And we'll see that in just a moment here. The proof of this law is omitted, but I encourage you to read it on pages 567 and 568. The proof is not that long, it's not that technical, but because there's already so much information to cover in this section, I decided to cut it and just leave it for you to read on your own. Okay, let's start with this. Let's try to solve an SAA triangle. So let me set up the example, and then I'll give you a minute to kind of think about it. On this triangle, we know three things. We know the length of this side is 5. We know the measure of this angle is 55. And we know the measure of this angle is 45. So because we know two angles and one side, that means we're going to need to use the law of sines. So first, what I want you to do is just think about it for a minute and think how you would approach this using the law of sines. Okay, now take a minute to just say something out loud to yourself about how you would approach this using the law of sines. You can say anything out loud just to kind of give your brain that feedback. All right, now let's do this one together first, and then I'll let you try the other ones on your own because we'll have a few examples. We'll have several examples in this section. So first off, because we know two angles and a side, we have to use the law of sines to solve for the missing information. But first off, because we know these two angles, we automatically know what C has got to be because the sum of the three angles of a triangle must add up to 180. So if we want to compute the angle C, we just do 180 minus the sum of the other two angles, and we get 80 degrees. So angle C is 80 degrees here. There we go. So now we have all three angles and one of the sides. We just need to solve for the other two sides, C and B. Now, the law of sines gives us this relationship right down here. So sine of 45 degrees over 5 is equal to sine of 55 over B, which is equal to sine of 80 over C. And now what you'll notice here is we can split this up into two equations that'll help us solve for the unknown. So for example, we can start with this, and I think I do start with this. So right now we know that these two values must be equal. And when we look at this equation, there's only one unknown value, and the unknown value is B. So we can solve for B using this equation. And then the next thing we can do is we can use we can use the first bit of information here and this piece that has missing information, and we'll be able to solve for C. So that's the general approach. Let's look at all the algebra here. Let's go through the calculations. Looking at the first pair of expressions, we have sine of 45 degrees over 5 is equal to sine of 55 degrees over B. Well, sine of 45 is actually one of those standard angles. So that one happens to be root 2 over 2. So this side of the equation just becomes root 2 over 10. Now we can solve this equation here for B just by essentially reciprocating and multiplying by sine of 55 degrees. And so we get this result. So that is what B is equal to. And at this point, the only thing you could do to make it any simpler really is to go to a calculator. But there's a couple things I want to mention about this. So first, this is the Approximation. So if you go to evaluate this expression here with your calculator or with any computational resource, Desmos, Wolfram Alpha, any of those things, it will only be able to give you an approximation. So that's one of the reasons that I have this little wavy equal sign here, because B is not equal to 5.7922. It's about 5.7922. And how accurate you need it to be depends totally on the context in which you're working. And this is one of the reasons that I emphasize keeping equality and not approximating until the very, very last minute. Try not to approximate ever if you can. And if you do have to approximate, try to push the act of approximation as far away as possible until the very last minute. So that's what I'm doing with this calculation. I'm keeping everything equal until the very last minute when I basically have no other choice but to approximate if I want to know, if I want to get like a decimal representation of something that's close to this value. All right. Oh, the other note I'll say is this. When you're using your calculator, remember to check to be sure that you are in the right mode. So make sure your calculator is in degree mode if you're using degrees, and make sure it's in radian mode if you're using radians. And at this point, I'm hoping that you're comfortable switching between both of those. We're going to use them kind of interchangeably. Sometimes degrees will be used, sometimes radians will be used. If there's no degree symbol given, you're supposed to assume that it's radians, right? So the degree symbol tells us that we're using degrees. Okay, now, all that aside, we've got B now. So now we just need to solve for C. And we can use the other relationship. So we can use this equation, which was the other two pieces. And then we can solve for C, and we get that C is approximately 6.9636. So now we've got all three angles and we've got all three sides. We have solved the triangle. Yay! Okay, now let's talk about ASA triangles. Oh, whoops, I forgot to put a pause here. So you'll have to do the next one on your own, I suppose. Actually, let me check. I did put pauses on some of these, right? Okay, I did good. All right, so let's talk about ASA triangles. In this case, what we know is we know two angles and a side again, right? Let me highlight these. So we know the angle A, the angle B, and the angle C. Because we know two angles and a side, we're going to have to use the law of sines. And the way we do it is very similar to what we just did. So first of all, because we have two angles, we already know what the third angle is going to be. In this case, it's going to be 135 degrees. So now we've got all three angles. We just need to find the two missing sides. How do we find the two missing sides? We look at this equation again, and we pick out the equations that we're going to use based on the information we have and the information we're missing. So what do I do on this one? Let me go to the next slide. Here we go. So here's breaking that equation into two pieces. And then at this point, it is really just algebra. So you can use any algebraic techniques that you know or remember. You're just going to try to solve for the missing variable, which in this case is A and B. Sine of 135, or I should say 135, is another one of those standard angles, right? 135 is a standard angle. It's 90 plus 45. So we can get at least an algebraic representation of the number right here. And then eventually we get these two expressions, or sorry, these two equations. There we go. So those two things that I highlighted in blue at the bottom there we go. Those are the equalities. So we know that A and B are equal to those values, and that's about as precise as it's ever going to get. So at that point, your only option is to approximate using some sort of computational resource. So I plugged this into my calculator, made sure it was in degree mode, and my calculator gave me this approximation right here. That A is about 1.9347 and B is about 2.3906. Oh, another little note, your calculator will generally be able to give you more digits of accuracy. So I think mine ends up giving me 10, I forget how many, maybe 12 digits of an approximation. But for this class, 4 is sufficient. 4 is sufficient. And I think the book only requires 2. But I feel like 2 is a little bit too little. So I usually try to use at least 4 decimal places of accuracy. Um, if you need more, go for it. If you need less, go for it. Really just depends on the context. All right, but that's it. So we solved the triangle. We have all 3 angles, we have all 3 sides. The triangle is solved. Okay, now let's talk about SSA triangles. So this is the situation where we know 2 sides and an angle opposite one of the sides. And this is what's known as the ambiguous case. This is the ambiguous case. The reason it's called the ambiguous case is because if you have this information, it's ambiguous. You don't have a single possible solution. You have multiple possibilities of solutions. So if you know 2 sides and an angle opposite, this could give you 1 triangle, 2 possible triangles that fit the data, or no triangle that fits the data. So there you go. This is kind of a picture of what the situation looks like. So in this picture, what we know is we know the length A, we know the length B, and we know this angle here. And if you have that information, it doesn't automatically give you a single triangle. You have to kind of go through using the law of sines to see which case you get. Here's all 4 cases here shown in uh, this is all the possible cases shown in just one picture. So here's the situation where you have no triangle. And what's happening here is basically the length A is not long enough to contact the opposite side of the side B. So remember, in this case, what we know is we know A, we know B, and we know this angle. But sometimes that length A will be too short, and so a triangle is not actually formed. So that's a possibility. Then we have 2 triangles. So sometimes this information will result in 2 possible triangles, and there's no way to get rid of one of them except in context. Maybe your situation makes it clear that you will need this triangle instead of this triangle right here. But there's 2 possibilities. And what's happening in this case is that the length A is longer than a straight edge, which we'll get down to right here. And so because of that length, it could basically swing inward or it could swing outward. And we have to consider both cases. So that's when you have 2 triangles. There we go. Then there's this case where you have a single right triangle. In this case, A is just long enough to contact that remaining leg at a right angle. At a right angle. So that's a possibility. You'll have 1 single right triangle. And then there's the last case, which is where you'll have 1 oblique triangle, or really I should say obtuse triangle in this case. So maybe that length A is long, and there's no way that it could swing back this way. Actually, let me erase this. Maybe this length A is pretty long, and there's no way that it could swing back this way to give you 2 possible triangles, right? So this length is so long that if we tried to swing it this way, it wouldn't actually form a triangle, right? So these are all the possible triangles you can get. None, 2, or 1. That's it. Okay. So the good news is this. So maybe as I'm going through this and as you're looking at the slides, your brain is like, whoa, what's going on? This is way too much info. The good news is you do not need to memorize these cases, and the law of sines will actually reveal which case is correct. So essentially, you have no idea which case you're gonna get, but when you start using the law of sines will reveal and it will basically eliminate one of the cases, or it'll eliminate the other cases until there's 1 possibility, meaning it could be no triangles, 2 triangles, or 1 triangle, as we're gonna see. So we'll do it case by case and see all the examples here. So we'll do this one first. Let's solve the triangle where we know that one side length is 2, another side length is 1, and one angle is 50. The angle opposite the side C is 50 degrees. So for this one, I just want you to think about it for a minute and just try to digest what the information is and what you think the triangle might look like. So just think about that for a minute. All right, now say something out loud about how you expect this to go. How would you solve this using the law of sines? Maybe try to recall what the equation is and see if you could figure out a relationship that would help you. All right, now try to write something down and see if you can get the first step on your own. See if you can solve for one of the missing sides or one of the missing angles. All right, now let's do it together. So here's how we start. The law of sines gives us this result right here. So we don't know angle A, we don't know angle B, but we do know some of the side lengths and we know one of the angles. So sine of A over 2 is sine of B over B, which is equal to sine of 50 over 1. So what we could do is we could solve for the angle A. Let's start with that. So what I'm doing is this. I'm going to use this information and this information right here because now there's only one unknown variable there. There's only the angle A that we don't know. So when I set these two equal to each other, I get this. And that tells us that the sine of A is going to be equal to 2 times the sine of 50 degrees. So at this point, you can go to your calculator and have it approximate that for you, and it'll give you 1.5320 approximately. But this is where something is off. Remember, sine is bounded, so sine is bounded by -1 and 1. So whatever the value is, of the sine value of an angle is, it has to be between -1 and 1. But here, this result is giving us a sine value that's 1.5. Over 1.5, right? That means there's no possible angle that could make this true. There is no angle whose sine is 1.5320. And that's something we've actually seen before in the inverse trig function sections, right? Was that 6.1 and 6.2? So this right here tells us there's no solution. There is no triangle that fits this data up here. This data is not sufficient to form a triangle. That's essentially what's going on here. Yep, the triangle can't exist. Pictorially, here's what's going on. So here's length C, or side C with length 1. Here is side A with length 2. And then here's the angle 50 degrees. And essentially what's happened here is the length C, which is 1, is too short. So no matter how we swing this piece to the left or to the right, it will never be able to contact the third side whose location is determined by this angle of 50 degrees. So that's how we know that there's no possible solution. There we go. No solution in this case. Okay, now let's do another example. This one is going to have one solution. So this triangle has a side length A equals 4, a side length B equals 3, and an angle A equals 60 degrees. So think about this one on your own for a minute. What could you do first? Okay, now say something out loud to yourself. What could you do first? All right, now break out the pen, break out the pencil, and try to work it out on your own. Try starting with the law of sines. Start with that equation and see what you can work out on your own, and then we'll do it together in just a moment. All right, here we go. So, right off the bat, the law of sines gives us this relationship. It's a good place to start. It's a really good place to start because it lets us see what information we have and what information we're missing. And then we just have to pair these results up and solve for missing variables. So what do I do first? I do this one first. And this relationship here, this equation, will let me solve for the angle B. So it's similar to what we did previously. Use this. Now I can solve for the angle B. First I solve for sine of B, and I get this. There we go. And sine of 60 degrees, well, 60 degrees happens to be one of those standard angles. The sine of 60 degrees is root 3 over 2. So we can get that the sine of B is equal to 3 root 3 over 8. And that's as equal as it gets. That's as accurate or exact as it gets. At this point, you can go to a calculator and it'll give you the approximation 0.6495. And the good news here is that that's actually possible. So this is not like the previous situation where we got a sine value that was not possible. Here, this is actually possible. So now we know that the sine of b is 0.6495, and we can use the inverse trig functions, in particular inverse sine, to find out what b is going to be. So here we go. There are actually two possibilities, so I should say that first. All we know is that sine of b is 0.6495, right? And there are two possibilities of angles between 0 and 180 where this is true. And let me draw a picture here just to make it a little clearer. Remember, our angles have to be between 0 and 180 because we're working with triangles, right? So we're essentially stuck here on the upper half of the unit circle, or just the upper half of the circle, I should say. Now, if we know that the sine of b is 0.6495, that means that the vertical displacement is 0.6495. So maybe the vertical displacement is going to be about here. That's a little bit much. It's going to be about here, right? And so now there's two possibilities. There's this angle right here. Actually, I'll call that B1, B1. And then there's this other angle here that goes all the way around. That's angle B2. Let me zoom in a little bit. It's kind of hard to see, sorry. Let me say that again and zoom in a little bit better here. So if we know that this is the height right here, 0.6495, we've got this possible angle, which is B1, or we've got this possible angle, which goes all the way around. That's B2. So we don't know which one is the possible, we don't know which one is correct. Maybe both of them are correct. We'll see. So what's the first angle gotta be, or the first candidate gotta be? It's gotta be this. So once again, what I did here was I went to my calculator, I made sure it was in degree mode, and I computed sine inverse of 0.6495, and it gave me this, 43.9873 degrees. So that's one candidate for angle B. Then we have the other one, so I did the same thing. Actually, no, I'm sorry. This time what I did was I took this result that I got for B1, and I did 180 minus that, right? Because that's what B2 would be, looking at this picture again. B2 would be 180 minus B1. And there's our two possibilities. So when I do 180 minus 43.9873, I get 136.0127 degrees. So those are the two possibilities. Now check this out. Check this out. We know that A is 60 degrees. So since A is 60 degrees, if we try to use B2 as our other angle, the angle that we want to be angle B, well, what happens is they sum up to a value that's larger than 180. So here, B2 plus the angle A is 60 degrees plus 136 degrees, which is about 196 degrees, which is greater than 180. So that means that B2 is not the correct choice because we need the triangle to add up to a total of 180 degrees. So B2 gets axed. B2 is not correct. So that means that B1 is the only option. Let me try that again. B1 is the only option. So now we don't need to label them B1 or B2 anymore. We can say immediately that the angle B has to be about 43.9873 degrees. Okay, now that we know what B is, we can find C by doing 180 degrees minus 60 plus 43.9873 degrees, which is about 76.0127 degrees. Again, you can definitely see that a calculator is needed for a lot of this stuff now, right? But there we go. Now we have all three angles, A, B, and C. We just need to solve for the last missing side, which is side C. So now we can do this. Oops, little highlighter. There you go. We can use this relationship here. Sine of 60 over 4 equals sine of C over C. Now that we know what the angle C is, there's only one piece of missing information, which is the side, little c. Once again, you solve for little c, And then you compute this, and you get that C is approximately 4.4818. And that's it. That's it. So notice here there was only one possible solution. So the first example was no solution because that length, that side length was just not long enough to actually contact. Here we ended up with one solution. And the reason we ended up with one solution is explicitly because of this situation. Oh, sorry, over here. Let me clear this for just a minute. Let me point this out. This is what eliminated one of the possibilities, this line right here. So when we computed the angles that were possible for angle B, one of them was essentially ruled out because it violated another condition of the triangle itself. And this is what got violated right down here. So this situation will, or sorry, this condition will not always be violated. And when that's the case, we end up with two actual possible triangles that fit the data. And so that's what we're going to see in this next example. All right, so let's take a look at this example here. Once again, we know two sides and we know an angle. So we're going to have to use the law of sines to approach this. So I'll let you think about it for a minute. So think about how you would approach it first. All right, now say something out loud to yourself or to your dog or to your family or whoever about how you would approach this. Even just one line will help, one spoken line. All right, now try to work it out on your own. Maybe start with the law of sines, see what information is missing, and see how you can solve for it. And then we'll do it together in just a moment. All right, here we go. Let's do it together. A good place to start is always just setting up the law of sines. So the law of sines yields this. This is the information we know, and we can basically pair off these relationships to solve for the missing information. What do I do first? Looks like I do this first, right here. So I use these two expressions and their equality to solve for sine of b. So if you solve this for sine of b, you get that sine of b is equal to this right here. There we go. Just some simple algebra, some simple arithmetic. Then you go to a calculator, and your calculator will give you the approximation 0.8264. So sine of b is 0.8264. That's totally possible. This is definitely a possibility. It's beneath 1, or sorry, I should say it's less than 1. So now we're going to use the sine inverse function on our calculator and get the two possible candidates for angle B. So evaluating this by calculator gives this approximation, 55.7306 degrees. And then if I do 180 minus that value, I'll get 124.2694 degrees. So those are the two possible candidates. Now, I think I say it here. Yes, yeah, I say it over here. So in either one of these cases, the angle A plus the angle B1 or the angle B2 will still be less than 180 degrees. Let's check really quick. Remember, angle A is 40 degrees. So if I do, actually one second, if I do 40 degrees plus 55, I'm still less than 180. So B1 is a possibility. But if I do 40 degrees plus 124, that's still less than 180. So B2 is still a candidate for the second angle. And because both of these candidates are valid, there are two possible triangles that fit this data right here. That's what that means. There's no way to eliminate one of them purely based on this data. If you needed to eliminate one of these two possibilities, that would have to come from the context in which you're using this approach. So maybe in the application that you're doing, there's no possible way that this could be the triangle. And if that's the case, then you can eliminate one of the angles right away and you get a single solution and you can move forward. But for us, we don't have that external context. We only have this data set right here that was given to us. And so all we can say is, these are the two possibilities. These are the two possibilities. So they're depicted right down here. Here's the first possible, or actually I should say, here's the first possible triangle. This one right here that I highlighted in orange. And you can see this fits all the data, right? Side length 9, side length 7, and then this angle is 55.7, approximately. So it could be that. Here's the other possible triangle. Here, here, and here. So side length 9, side length 7, and then this angle right here is 124.3 degrees, approximately. So this is kind of like the this is literally the last possibility, right? The first example was essentially showing us that let me do this, that whatever this side length is, if it's too short, you don't get a triangle. If it's exactly long enough, you'll get a single right triangle. Or if it happens to be a little bit longer than that, then there's two possibilities. It could swing this way or it could swing this way. That's what's going on. So this is why this is an ambiguous case. Again, none of this needs to be memorized. All of this information just comes out of using the law of sines. So once you have the law of sines and you kind of just walk forward and follow your nose, everything falls into place. Everything falls into place. All right, so now let's proceed. Let's go with B1 first. So what was B1 again? Sorry, I got too much stuff on this page. Let me erase this. B1 was what value? This. Okay, so we're going to do this triangle first. There we go. So if we look at B1 first, then we can solve for everything else. So the angle C1 is going to be 180 minus the sum of A and B, or I should say sum of A and B1. So this tells us that the last angle has to be 84.2694 degrees, approximately. Then we can use this information in the law of sines again. And this lets us solve for the side C1. And we get that the length is 10.8356. So that would be this length right here. This length is approximately 10.8356. There we go. And this angle right here is about 84.2694. Oh, another thing to keep in mind, these figures are not drawn to scale. They're not drawn to scale necessarily. And actually, hold on, I apologize. I'm sorry. That is not the correct angle. That angle is 40 degrees. Bleh. This angle, this angle is 84.2694. There we go, degrees. But again, these figures are not necessarily drawn to scale. Certainly the figures that I sketch by hand are not drawn to scale. So do not let a picture fool you into thinking that that's actually what it looks like. It looks like the book is trying to keep a scale just so that it's very intuitive, but remember, there's no guarantee that these things are to scale at all. Okay, so that's what we do, or that's what we get if we choose B1. So now we've solved this triangle, the bigger triangle, this one right here. Now let's choose B2 instead. So if we choose B2 instead, we get that the angle C2 is about 15.7306. So that's this angle right here. There we go. This angle right here is about 15.7306 degrees. Now we can use the law of sines to find the missing side length, 2.9524. Actually, let me go back to this real quick. Yeah, there we go. So this length right here is about 2.9524. There we go. And now we've completely solved the second possible triangle, which is this one. All right, there we go. So we've seen all the possible cases, and here's both of them all put together. These are both triangles just shown put together. These are the two possibilities based on this data. And like I said, that's as good as we can do. If you've got some other information that eliminates one of these cases, great, then you got a single case. Okay, on that note, let's take a look at an application. So one of the cool things about the law of sines and the law of cosines is that it lets you solve for things that you really, really wish you could find, but without trigonometry, you can't really do it. Right triangle trigonometry. So here's a really fun example, I think. If you ever wondered like how they do this, this is essentially how they do it. If you want to measure the height of a mountain, a surveyor takes two sightings of the peak at a distance 900 meters apart on a direct line to the mountain. So there's basically a direct line to the mountain. And what the surveyor does is they take a reading here and they take a reading here. And what they want to know is they want to know the height of the mountain, the total height. Like, how tall is that mountain? That mountain over there or whatever. Like, how tall is it? That's a good question, right? Well, what you can do is you can basically set up a transit. Oop, there we go. You can set up a transit right here, take an angle reading, and then move closer to the mountain, and then take another angle reading. And then using the law of sines, you can get a height for that mountain. You can get a height for what that mountain is. So in this case, the first observation gave an angle of elevation of 47 degrees, and the second one gave an angle of elevation of 35 degrees. Now, if we know that the transit is 2 meters high right here, if the transit is 2 meters high, what's the height h of the mountain? Okay, so here what I want to do is you think about it for a minute. Think about how you could use this information and the law of sines. All right, now say something out loud to yourself. What would you do first? Okay, now try it on your own. See if you can solve for h. You're probably going to use the law of sines, so I always recommend starting there. See if you can figure it out, and then we'll do it together. All right, here we go. So drawing a sketch always helps. There's a sketch here on this picture as well, but drawing a second sketch that is really just like a schematic can help clear things up even more. So we have all the information that we're given plotted on this picture. This is the unknown, h. This is the length that we want to know. We also know that the transit is 2 meters high. So what we really want to do to solve this problem is to find this length b right here. Because if we can find that length b, then we can find the length h just by adding 2 to it. So how do we find the length b? Well, what could we do? What could we do? Well, we've got a triangle here. We've got two angles and we've got a side. So the thing that we do know is we know this right here. We know the angle C because angle C is supplementary to the angle 47 degrees. So that means that C plus 47 is going to add up to 180. So that tells you that C has got to be 133 degrees. Now what we've got is we've got a side and two angles. So that lets us solve for some other information, because what we really want to do is we want to get at this side length B, but now we can find this. We could find the length C here, and that'll lead us on the way. We also know that the angle A is 12 because we found two of the other angles. Well, I'm sorry, we found one of them, but now we know that uh, angle C is 133. We already had 35, so now we can solve for angle A to get 12. Okay, here we go. Now, using the law of sines, we start with this relationship here. Plug in what we know. We know sine of 12, or sorry, we know that angle A is 12 degrees. We know that this length is 900, so we get that. We know that this angle is 133, and we don't know this length, so we don't know the length C. But we can solve for it. So if we solve for C, we get this. And then we go to a calculator and we get an approximation, and the calculator approximates it as 3,165.86 meters in this case. So that's this length right here. 3,165.86 meters. So now we're one step closer. Actually, what I'm going to do here is I'm going to pause again to see if you can figure out what to do next. Remember the goal here. The goal is to find B. So how could you find the length B with the information we're given here? Think about it for a minute. Okay, now let's see if you were right. Okay. Remember, right triangle trigonometry is really helpful, right? SOHCAHTOA. And what we know is we know this information right here. We want to know this information right here, and we know this angle. Well, if we look at the big picture, the right triangle right here, we can find B by using right triangle trigonometry because we know that sine of 35 is going to be, what is it, SOHCAHTOA, opposite over hypotenuse. So sine of 35 is going to be opposite over hypotenuse right here. There we go. We know what C is approximately. C is about 3165.86. So now we can solve for B. B is going to be approximately 3165.86 times sine of 35 degrees. 35 degrees is not one of those standard angles, so we can go to our calculator, have it evaluate sine of 35 and give us an approximation. And so B will be about 1,816 meters. So that's what B is. That's what B is. This piece right here. That's 1,816 meters. Then we have to account for the height of the transit itself. So the transit is 2 meters tall. So that means that the height of the mountain, H, has got to be 1,818 meters total. And that's it. Pretty cool, huh? I think that's pretty cool. What did we do to actually determine the height of this mountain? Well, go back to the picture, right? Check this out. Come here. There we go. Um, Literally, you just take your transit and you spot the mountain from one angle, right? You measure the angle, and then you scoot forward about 1,000 meters or so, right? And then you do it again, and just with that information, these two angles and then this length, and then of course the height of the transit, I should say, you can determine the height of the mountain, which is really cool. So it's not like you have to drill a hole in the mountain and drop a tape measure down or anything like that. You can just use some basic measurements and the law of sines. Super cool. Okay, so on that note, let's play. You should go try the homework now. That's it for this section. One thing I'll say is, like I said, this is a very technical section, so thanks for bearing with it. The next two sections are not as long, which is kind of nice. The law of cosines is super cool. And then the very last section, or I'm sorry, the next section after that is 7.4. Yeah, 7.4, and that one's about area, so it's not too bad. But I won't keep you much longer. There we go. I got that pulled up. I'll say bye and I'll see you all next time.